So the dot product is I guess our second attempt of some sort of multiplication that involves vectors. We know that when we add or subtract vectors, we get another vector. In fact, I sometimes like to make a little chart about some operations, binary or otherwise, operations for vectors that that give you the type of thing that it results in. So when we're adding or subtracting, we could take a look at adding a vector or subtracting a vector from another vector, and then your result is a vector. And so those are the first two simple operations that we did yesterday when we talked about vectors. And then we talked about scalar multiplication when we have a scalar multiplied with a vector, and then we get another vector. So I don't know if people would necessarily call this a true multiplication when we're talking about vector operations, because it's combining two different things. And so when we begin talking about multiplication, the first type of real multiplication that we have between two vectors is the dot product. And the interesting thing about this is that when we take a vector and then we dot it with another vector, we result in not a vector anymore. Our result will become a scalar, and we'll see that in the definition, and then we'll see that in some of its applications. Now, there's another multiplication that we're going to study, and this multiplication is a special type of multiplication between two vectors in that it only really works with three-dimensional. We can coax a two-dimensional vector into this, but beyond 2 dimensions, or beyond 3 dimensions, sorry, beyond 3 dimensions, this idea of this cross product, another product that we're looking at, is going to be a lot more difficult to define. And so for us, we're going to be just looking at these things in 3 dimensions. And this will result in a vector. So we're going to explore these two multiplications. The first one, the dot product, we'll talk about today, and then the cross product we'll talk about next time. And those are, in fact, the names, the dot product and the cross product. And sometimes the dot product is called the scalar product. And sometimes the cross product is called the vector product. Because of the result that you get when you perform those multiplications. So again, our focus is this today, the dot product. And today we're going to try to define the dot product in a couple different ways. Now, a lot of textbooks, including this one, define it one way, and then the other way becomes like a theorem or something. Some books define it geometrically, and then they present the algebraic as a theorem. But I'd like to just think about both of them as both definitions of the dot product, and when we combine those two, we get some nice applications, like finding the angles between two vectors and stuff like that. So let's get on it. Let's define the dot product and see what it says. Now you could do this in separate slides, but I think we could just put this all in one. The algebraic and the geometric definition of the dot product. Algebraically, a dot product is an easy computation, and this is where we would multiply the components of the two vectors together and then add those results together. Now that's an interesting approach to the dot product, because clearly your result is now a scalar. And you can see that when you take the components, which are scalars, you multiply them together, they're going to be scalars, and then you add 3 of them, then they're still going to be scalars. By the way, you could do this in 2 dimensions as well, and you could do this in 5 dimensions. So it seems like it's fairly extendable to looking at this beyond 3 dimensions. And that's another nice thing about the dot product. And the dot product, we'll see after some of the properties, it's a good way to measure things between 2 elements, 2 vectors or whatever. Now, the geometric definition is a little bit trickier, and what they do here is, I guess you would need some geometry involved here. And so what they do is they identify the 2 vectors, and in general, when we want to work with a couple of vectors, remember these vectors could just be floating around in space, but we can put them in standard position, or we can put them in any position on the space or plane that we're working on. But in general, when we want to work on a couple of vectors together, we put them tail to tail like this. And when we do put them to tail to tail like this, we can identify an angle between them, and this is the theta that they're defining. So when they say theta is some angle between A and B, they're assuming that A and B are vectors that are put tail to tail. And then the dot product then becomes the product of the lengths of the vectors A and B times the cosine of the angle between them. Now, like I said, we're presenting that as a definition, but if you want to find a relationship between these 2 definitions, you can look at the book. Our textbook defines the dot product as this algebraic definition that we have, and then they go on and they say this is a product or a property that comes out of that definition. And so you can look at the geometry that they use to prove that this is actually, in fact, true. And it will have something to do with some projections that we'll talk about later on. Okay? So that seems reasonable enough. Let's take a couple of vectors as an example and find the dot product between them, and then maybe even find the angle between them. So let's come up with a couple of vectors. Let's just make it up. What's vector A? 1, 2, 3. And what's vector B going to be? Oh, really? Okay, fine. So we have these 2 vectors, and let's first compute the dot product. A dot B is going to be, again, component by component. You would multiply them. 1 times 4 plus 2 times 5 plus 3 times 6, and that turns out to be 32. Yeah. Again, it's a scalar, it's a number, so that's it. Okay, so that's 32, and then let's say we're interested in finding the angle between these 2 things. If we're interested in finding the angle between them, we know that the angle between them, maybe I should do this in a different color. So maybe the angle between them is, I don't know what it is. So we know that if we take the dot product, it's going to be equal to each of these magnitudes times the cosine of the angle between them. By the way, the right-hand side is a scalar because magnitude is a scalar, magnitude is a scalar, and then the cosine of some number is going to be a scalar. And so this is, at this point, the unknown. This is what we're trying to find. And so we're just going to, since we know A and we know B, we can easily take the dot product, we can easily find the magnitude, and then we just solve for theta. So we know that A dot B is 32. We got that from our previous calculations. And then we find the magnitude of A. I think that's 9, 13, 14, square root of 14. Square root of 14. And then B is, now these are bigger numbers, 36, 25, and 16. What? 77? We agree? Yeah? And then we have the cosine of the angle between them. And so if we solve for that, cosine theta is equal to 32 over square root of 14 square root of 77. And then you find the inverse cosine. Then you would get your result. Now, I guess this is a good opportunity to do some trig, and this was going to be the warm-up problem that I was going to give you, but I didn't feel like grading warm-ups anymore. So let's think about the arc cosine as a function and the values that it's going to give out. And then we'll come back and take a look at those vectors again and what the angle actually means. As an aside here, a little trig flashback. Let's call it f of x equals arc cosine of x. As a function, it's always nice to know the domain and the range of things so that we know what things we can input and we know what to expect as outputs. So do we know what the domain and range are of this? Now, as a function, as an arc cosine function, they have a specific domain and range. And we'll take a close look at the graph after you guys tell me what the domain and range are.
Domain, we're talking about the accepted input. That would be the ratio of the size of the triangle plus from -1 to +1?
That would be the domain.
Yeah. For the range, it's got to be all angles. So that one I'm a little confused. 0 to 2 pi is only one iteration of that actual, keeps going. So you say 0
infinity pi. Okay, let's talk about the domain first. Your deduction is pretty good. Let's talk about the domain. The idea that you can only put in numbers between -1 and 1. So when you calculate 32 divided by root 14 over root 77, you should get a number between -1 and 1, because if you don't, then something's wrong. Right, so that's an important part in this business that we're dealing with. The range, when you go from 0 to 2 pi, think about the cosine function. This is the inverse of the cosine function. Think about the cosine function, and the cosine function, as a function, passes the vertical line test. Sure, that's what happens. But as a one-to-one, I don't know if we talked about one-to-oneness in this class. I think we did one time. As a one-to-one function, the function is not one-to-one. And so for you to be able to invert a function, that function has to be one-to-one, which means that cosine function, which is a sinusoidal function that goes on forever, has to be chopped so that you can, reflect it about the y equals x line, and then you're going to get a function. Because if you take that whole cosine function and you don't chop it, and then you do the reflection, then you have the sinusoidal function going along the y-axis, which is clearly not a one-to-one function. So we need to know how to chop it, where to chop it. So if you imagine, I'm going to erase this, but just going from 0 to 2 pi, because that's a good sampling already. In fact, it's not going to be all of that because it doesn't pass the horizontal line test. We have to find a good place to chop it. And in terms of inverses of things in math, they talk about these things called branches, because really we can chop it anywhere we want so that it passes the horizontal line test. But there's a certain convention for chopping functions to find inverses. And the convention for the cosine is?
Are you thinking from 0 to pi over 2?
Close.
0 to pi?
So 0 to pi over 2 stops you here, but then you really want to get as much out of it as you can. So we're going to go all the way to pi. And so that will turn out to be the output for this. So your range is going to be from 0 to pi. And then now, if you were to draw this graph, now think about just looking at this part of the cosine graph and then reflecting it about the y equals x line. You can imagine trying to draw it along the y-axis, kind of sideways, and this is what you would have. So you have the arc cosine function, domain from -1 to 1. So we know if in your calculator you try to put arc cosine of 2, it's going to give you an error, right? Because that's not part of the domain. You can only put numbers between -1 and 1. And then the output will be the thing from 0 to pi. Now, what's interesting here is that when we're looking at the outputs, it kind of depends on what you're inputting here, right? Does that make sense? Yeah. So looking at this graph, we can take a look at how the input works. First of all, you're only going to get a number between 0 and pi for this. So in terms of an angle between two vectors, does that make sense that you can only get between 0 and pi? I mean, the vectors, you know, if you look at two vectors, you can go from 0 to 2 pi. Think, is that okay to just go from 0 to pi? Yeah, I think so. There's a couple of nodding heads. Now, if you look at an angle between two vectors, random vectors that we kind of drew, it would make sense that your angle would just be between 0 and pi. Because if we went past 2 pi, or if we went past pi, you're looking at this angle over here. Well, so really, if you have two vectors, you can define two angles. So when you're doing the dot product, you're always going to be looking for the smaller of the two angles. Okay, unless it's 180 degrees, in which case you'll get pi. All right, so that's one interesting thing about this. The other interesting thing about this is that if you look at the formula for the geometric definition of the dot product, the right-hand side over here has magnitudes of A and B. When we do this computation and then we solve for we're solving for theta, right? We're going to take the cosine inverse of this. We're going to take the cosine inverse of the dot product divided by the magnitudes. Now, the magnitudes are always positive, right? So the dot product, we haven't come up with it. I was actually I should have put a negative sign over here, but you can have, it's possible to have a negative number for the dot product. So as long as, in your formulas, your dot product divided by the two magnitudes will be a number between -1 and 1, then you should be able to find the angle between them. Now, it turns out that if your dot product is negative, what can you say about the angle between the two vectors you're looking for? It's what? It's what? No. You can never have anything over 180. We've just kind of established that. But it's larger than something else. It's larger than 90 degrees. It's larger than pi over 2. So this gives us some interesting information to try to look ahead. It's one of those things that you could check yourself with. Some results based on knowing about the arc cosine function, if you know about that, that if the dot product A dot B is bigger than 0, it's a positive number, then we have an angle that's less than 90 degrees. If A dot B is less than 0, it's a negative number, then according to the graph, we're between pi over 2 and pi. And I think that's called obtuse. And we know that we can only put numbers between -1 and 1, and assuming that your magnitudes will shrink your dot product down to a number between -1 and 1, we're just now in this missing this other possibility. If A dot B is actually equal to 0, then what do you get? Right angle. And so this gives us a nice property for checking for orthogonal angles between two vectors. If you have two vectors, you're suspecting that they might be orthogonal. If you take the dot product of those two vectors, they should equal to 0, regardless of their length, right? Because you're dividing by the length. It doesn't matter what the length is. If you take the dot product, it's going to be 0. And if it's equal to 0, then the angle between them, we know that cosine of 90 degrees is equal to 0. So that's the only possibility. Okay? Pretty cool, huh? Yeah.
So if we had multiple, let's say we have like a negative AC factor, and would that mean that like all the angles are perpendicular?
If the dot product's equal to 0, if you have like two vectors, if you have three vectors, and their dot product's equal to 0, then yeah, that means they're all perpendicular to each other. As many vectors, except, you know, if you're sitting in R3, you're just in 3 dimensions, then you can have 3 vectors that are orthogonal to each other, but if you introduce another vector, then that's not, there's no way for that 4th vector to be orthogonal to the other 3. That, again, is a linear algebra problem that if you're in that class, that you'd have to try to prove. Okay? All right. There's an interesting problem that I had when I was in college, and it was like a advanced linear algebra class, and the professor said, here's a little linear algebra test. If you don't pass this test, then you shouldn't be in this class. And one of the problems there was an interesting problem. He asked what was the angle between an edge of a cube and a diagonal of a cube. What was the angle between those two line segments? And so I thought, edge of a cube and diagonal of a cube, that's 45 degrees, right? Well, I guess if it was a square in 2 dimensions, it would be 45 degrees. That's fine. But a cube is in 3 dimensions now, so that's a little bit more difficult to gather. So any edge of a cube would be a good thing to look at. And so the easiest probably edge of a cube to look at is the edge of a cube that's maybe along the x-axis or something. And then the diagonal of a cube would go from one vertex to the opposite vertex, and the drawing here looks like the red arrow is a lot smaller than the purple arrow, but because of the perspective, the red arrow is actually longer. But that's besides the point. So we're talking about a cube, and as long as the cube has the same sides in the x and the y and the z, we can call it 1, or we can call it any number, but as long as those numbers match up, then we can find the angle between them using the dot product. So let's say we have a cube of side length c, and then I'm looking at 2 vectors, and I want to find the angle between those 2 vectors. And now that I draw this, it's not looking so 45 degrees anymore, right? And so let's see if we could do this simple calculation. If we know the vectors, and we do, is C00 and CCC, then it's just as simple as using the dot product formula. So let's find the angle between them. Let's just go straight to the formula. Theta is going to be equal to the cosine inverse of the dot product of C00 and CCC is what's going to go in my numerator. So the dot product looks like it's just going to be C squared. Is that correct? Now, the denominator is going to be the square root of c squared plus 0 plus 0, I mean 0 squared, and then c squared plus c squared plus c squared. So I'll have a c for the first one, and I'll have a c squared under a square root, which is another c for the second one, and then I have 1 plus 1 plus 1, which is 3. So if you somehow simplify those 2 things into this, you'll get those values. And so I have 1 over root 3. Which turns out to be, not one of those nice angles. You actually have to put in your calculator and figure it out. But when you figure it out, you'll see that it's not 45 degrees, not 90 degrees. It's somewhere in between. Anybody know what it is, approximately? Say it again? So, depending on if they're asking you your answer in degrees and radians, you have to be kind of flexible in this class to be able to easily switch your calculator into those different modes. And so sometimes when you're doing homework, they're interested in radians. Sometimes when we're doing physics problems, they're interested in degrees. So you should be able to catch those things. All right. Any questions? Oh, I think I was going to bring some tetrahedron and polyhedron class, but I forgot. It would have been good to talk about vectors using those things. Anyways, maybe next time. Maybe never. So, I think there's some pretty important properties of the dot product. I think there's some important properties of addition and multiplication that I didn't, or addition and subtraction that I didn't mention last time. But we're getting to dot products. I think it's kind of important to start talking about these things. And in general, I just list these down and maybe talk a little bit about them and then just move on. But I think it might be good to think about possibly proving some of these things, because I think they might be worth proving. And the proofs of these things are pretty basic, I think, and you kind of set the vectors into equal to some generic vectors using letters. A sub 1, A sub 2, A sub 3 are the common ones that they use. So maybe we can prove one or two of these things and then make comments about the rest of them. Now, this notation, I don't know if we've introduced this notation in class. This is our notation for the vector space that we're talking about. And here we're talking about a vector space in 3 dimensions. Now, we're talking about dot products, and it turns out that we can also talk about dot products in R2 as well. But we can also, with the dot product, we can also talk about these things in any dimension that we want, it turns out. We can define, well, it's defined for us, some of these things. I mean, maybe the length is not exactly defined in higher dimensions, but the definition can just be extended in higher dimensions, and so we can get them set up. But I think this first one is an interesting fact, property to think about and then prove. And then I want to also make comments about the last one, because I think that last one is also interesting. And the notation there is carefully presented to you. And I want to make a big deal about the 0 versus the 0 vector. All right, let's talk about the first one and prove it. So a lot of times for these basic properties, we have a definition of something, and then we have representations for the things that are defined. And so in general, we can just let A equal to ABC or A1, A2, A3 or whatever, and then work with that to, based on the definition of the dot product, based on the definition of the magnitude, we'll see it all come out. So if we let A, the vector A, equal to the components A sub 1, A sub 2, A sub 3, and then we don't need a B, but if we did, when we say let B equal to B sub 1, B sub 2, B sub 3. Anyways, here in this case, we just need A. Let's take the dot product of A with itself, and we're going to get A sub 1 times A sub 1 plus A sub 2 times A sub 2 plus A sub 3 times A sub 3. I mean, we don't really need this next step, but just to make it look like kind of like as a step into the right-hand side, this just looks like the magnitude without the square root. Or if we impose a square root and square it again, then we're getting the same result. And that is equal to the magnitude of A squared. So this is a simple proof of a simple property that may have big implications for us later on. So we'll use this particular property a little bit later on as we start digging deeper into into our multivariable calculus. The other property that I wanted to make a big deal out of is the last one. And if you look at the last one, there's two zeros that are involved there. One of them has an arrow on top, and the other one does not. So the one that has an arrow on top is a big deal, because whenever you have an arrow on top, that's represented as a vector. So because that's a vector, the zero vector is actually a vector depending on where you live. In this case, we live in R3 right now. That vector will have three zeros in the three components. And then using the same A, like A1, A2, A3 that we have, zero vector dotted with A is equal to 0 times A1 plus 0 times A2 plus 0 times A3, which is equal to 0 plus 0 plus 0, which is equal to 0. And now I don't use vector because this is just a number. This is a scalar 0. Okay? At some point in time, there will be cases where we're looking at 0, and then I'm going to ask you to identify, is that a 0 vector or is that a 0, 0? It's 0 scalar, right? And you should know whether something's a vector or a scalar. Any questions? All right. So let's take a look at some applications to the dot product. And the first one is this whole idea of projection, which is an interesting application. And it turns out that this will end up being useful for us later on to create more formulas of things like distances. Because distances, we're interested in the perpendicular distance of something from a point to a line, for example. And the projection is one way to get there. Let's start by looking at a couple of vectors. And let's put them in this scenario again, tail to tail. And let's say we have vector A and then B. And we may be interested in the shadow. So imagine shining a light up on top and casting a shadow down below. And then we get a vector, or just a length, that we might be interested in. So it turns out that this might be important for us for certain cases, and we want to identify this thing as either a vector or a length. Either of those might be useful. So let's first look at it as a distance that we want to find. So what's the length of this vector? Well, how would you find the length of that? Oh, so there's some cosine theta. So if we introduce this angle between them, and we know the vector A, and so we must know the length of that vector. the length of that vector is the magnitude of A, then we can use some sort of trig, right? Adjacent over hypotenuse kind of business, and the adjacent is what we're looking for. So the length of this thing, Caroline, what was it again? A, well, the magnitude of A times cosine theta. Right? Okay. Well, we weren't really given the cosine of theta, right? We just kind of threw that in there. So let's just say, can we replace cosine theta with something? I mean, we can leave this as our formula, but if there's a way to, you know, to not take the step of having to find cosine of theta, it's the geometric definition, right? So if you look at that geometric definition and in your head or in a piece of paper solve for cosine theta, you get the dot product divided by the magnitudes. So let's replace cosine theta with that. Looks like the A's would cancel, and then just A dot B divided by B. So this length over here has a special name, and this is the, let me write it in words, component or scalar. Let's put scalar in parentheses. Projection of A onto B. And the symbol for this is COMP for component, projection of A onto B, and B becomes a subscript. And this is equal to, as you can see here, the dot product of A and B divided by the magnitude of B. Because the magnitudes of A canceled, right? So that's the length of that vector. And the length, in fact, is a scalar, right? So sometimes this is called a scalar projection. It's a projection that you get, but you're taking the scalar portion of that. Does that make sense? Now, some occasions you might be interested in the actual vector. You might be interested in the actual vector, not just the length of this, but the actual vector. So we know that the direction is B. We know that the direction is B, but we want the length of this vector to be B dot A divided by B by magnitude of B. So this is a problem that we had yesterday. What? Make B into a unit vector and then just multiply it by this, right? So to find the actual vector, with length A dot B over magnitude of B, you're going to make B into a unit vector. and then multiply. Scalar multiply. So what's your vector going to be? Your vector is going to be A dot B divided by a magnitude of B times the vector B that's made into a unit vector. How do you make something into a unit vector? Divide by its magnitude. There you go. So now you have the formula. Okay? And what is this? This is called a vector. Vector projection of A onto B. And then this time the notation is a little bit different. PROJ, projection of A onto B. Now I say that in that order, and I write it in that order. So I'm writing A first, and then I write B as a subscript. If you can get used to doing that, this is big. So the biggest thing here is to confuse A and B and to figure out which one goes in the denominator and stuff, because you'll see in the formula, when you look at the formulas, where it's being projected onto, that's a subscript, that's what goes down in the denominator. And so this formula is going to essentially equal to this thing, A dot B divided by B squared. And then, so I put the second magnitude of B here as part of the magnitude of B for the scalar. And then this is your vector. So this is how the vector is shown. So this vector projection results in a vector. The scalar or component projection results in a scalar. And the magnitude of this vector projection is in fact going to be whatever the scalar projection was. So depending on what is being asked of you, you're using one of these two formulas for the projection. Okay? Any questions?
What's up with the vector projection? Why exactly is that done?
Well, since we know the length of that vector projection, we just multiplied the length of the vector projection by the unit vector in that direction. And we simplified it, worked it out, and this is a formula that you would normally see if you Google this or if you look at this in your book. But to see where it comes from, I think you might remember it a little bit better. And remember what goes in the denominator here, right? B squared, not A squared. In fact, according to one of the properties, we can rewrite this bottom as what? Not that it's usually written that way, but we can. A dot B over B dot B. Don't cancel the B's. Dot products don't work like that. Is this a dot product over here? This dot? It's a scalar multiplication. This is a scalar times a vector. These two are dot products because these two are vectors. So that's the other thing that's going to be popping up every now and then, is that I'll put a dot, say I'm multiplying these two things. You should identify, is that a regular multiplication of scalars? Is that a dot product, or is that a scalar multiplication between a scalar and a vector? So it's always good to identify what you have there, is that a vector, is that a scalar, and then identify what kind of multiplication you're dealing with. Okay? Are you okay? You okay? Is this giving you guys a headache? It gets kind of confusing. For your homework. If you have a line and a point in space, and you're trying to find the distance between that point and that line, you're going to want the shortest distance, which is a perpendicular distance. So somehow this idea of a perpendicular distance, this perpendicular drop over here, is going to be the tool, the projection is going to be the tool that we're going to use to find that distance. And since we're not in lines and planes yet, that's later on in this chapter. I'll keep you in suspense. Not that you guys will be in suspense, because you probably don't care right now.
So the scalar, or the component is a scalar, and then the projection is a scalar times that.
Which gives you a vector, yes.
Gives you a number.
Yes. All right. I don't know if I had a homework problem picked out. Let's see if we can find a homework problem. Oh, number 8 looks interesting. But number 9 is the one with the projection problem. What? Well, as an example, I would do number 9, but it's just putting in stuff in the formula, so can I just not do that and say that I did? All right. Let's take a look at number 8, because that looks kind of interesting. Find two unit vectors that make an angle of 60 degrees with V. How do we do that? So this will require the dot product, clearly. We're in the dot product section. And we're in 2 dimensions, so it makes it a little bit nicer for us to deal with. So we have this vector V. And we want to find 2 vectors. It looks like there will be 2 vectors, right? That kind of makes sense. Let's call the vector A. And then there's another one on the other side, but I think if we just try to find one of them, that'll help us deal with that, finding the other side. So what we're going to do is we're going to, you can really do this without the dot product and just use some guessing and checking and using lines and stuff. But let's take a look at this using the dot product. And let's assume that A is equal to AB. I hope my A with no arrow and the A with the arrow look different enough for you. to say that this is a vector and this A is a scalar. So if we're going to use a dot product to do this, we should know that the angle between them is going to be equal to the dot product divided by its magnitudes. So we can assume that they're unit vectors from the beginning, and then we'll deal with that assumption a little bit later on. But now for this, let's let cosine of 60 degrees equal to V dot A divided by the magnitude of V and then the magnitude of A. And then since A is a unit vector, let's assume that the magnitude is equal to 1. And then it's a unit vector, that means A squared plus B squared is equal to 1, right, because of the magnitude business. And so we might need that information later on. So V is equal to 4,3. A is equal to AB. And so we have 4A plus 3B is equal to, and then whatever the magnitude of this is, 12 and 9, not 12, 16 and 9, 25. Now, what's the cosine of 60 degrees? Half?
No one.
Okay. So it's 1/2. And so if we continue to work with this, we can multiply both sides by 5. So we got 5 halves is equal to 4A plus 3B. We have 2 unknowns. We have 1 equation, or do we have 2 equations? What's the other equation? Doesn't look like an equation. Speaking of my A's. So the magnitude of A is A squared plus B squared under square root. If that's equal to 1, then A squared plus B squared is equal to 1. And so now you have 2 equations and 2 unknowns, and you can solve for this any way you want or can. Or what? You can use matrices. Actually, you can't because these are squared, so we're kind of in a jam here. So we call on Wolfram Alpha to save us, usually. That's what I'm going to do. So we're asking Wolfram to solve a couple of equations. Let's put the couple of equations in another parentheses here. We got 5 halves. Oh, by the way, if you want decimals, then you can use decimal notation. If you don't use decimal notation, Wolfram is going to try really hard to keep it as an algebraic number with fractions and stuff. So let's make it work a little bit here. 4A plus 3B. And then the second equation is 1 equals A squared plus B squared. And for you computer people over here, you really should be using equal equals, because equals and equal equals are 2 different things. But Wolfram, over the years, have developed this nice, friendly language where you can type in what you feel, and then it'll try to cater to your feelings. That probably wasn't the best words to describe that, but so in algebraic notation, this is its attempt to try to keep it as non-decimal as possible, but the decimal looks like it's going to be negative 0.11 and negative 0.9. And we should expect two equations or two solutions for this. We have two equations and two unknowns, and here's the other pair. We got 0.9 and negative 0.3. And if you imagine or even draw that out, you should see that it would look generally be 60 degrees from that vector 4, 3 that we have. So let's take this and put it in our notes. Oh, yeah. Oh, it came from the fact that this is supposed to be a unit vector. So because it's a unit vector, it has to satisfy that thing. It has to be equal to 1. Yeah. And so this is the length, and a squared plus b squared under a square root, and then you square it, it's just equal to 1 anyways. Yes?
How would this problem be different if we didn't use the unit vectors limit? It just says like find two vectors.
Well, then you would more or less guess and check because this vector would work, this vector would work, this vector would work, and then now you have an infinite number of vectors to deal with. So making it into a unit vector kind of just restricts it to just exactly 2 answers. And so that's what we have. That's why they want a unit vector. All right. So you guys have homework or something? There's going to be a quiz on Monday morning. Tuesday. Oh, Tuesday. Okay, fine. Have a good weekend.